Berkeley. So,
hi.
Yep.
Hi, everyone.
Hi.
I'll just share my screen. Can you see my screen? All right.
Yep.
Good. Right. I'll get started. So it's great to be telling you about this work at this reunion. Actually, I think that it fits well because it is a result of a collaboration that started during the quantum wave semester last year. So I'm very thankful to my collaborators, James, Dakshita, and Fermi. Basically, after the pandemic hit, we started meeting every week virtually. So I've definitely learned a lot from them. I can say this has been, for me, one of the bright spots during this pandemic, something that I looked forward to every week. I'm also actually thankful to Simons for the great idea of putting the lattices program together with the quantum one. In fact, James, Dakshita, and Fermi were all formally participants in the lattices program. So before starting, I should also say there is a concurrent and independent work, 2 hours, which proves the same result with a bit different techniques by Alex, who's here, Rachel Lin, Fan Song, and Vinod Vaikunthanathan, which I believe is also the result of a collaboration that started during the semester at Simons. So in this talk, I'll be focusing on our own work, since this is the one that I know best. So our work establishes that one-way functions imply secure multi-party computation in a quantum world. So let me start by telling you what secure multi-party computation is. So in this setting, there are a number of parties who can talk to each other, each with a private input, xi. So the goal is for them to compute a circuit C on their joint inputs. So C takes as input x1, x2, x3, and x4 here. And the parties are going to do this computation by talking to each other, so by exchanging messages. And at the end of the protocol, each party should receive the output of the circuit on the joint inputs. So this is the correctness requirement. And there's also a security requirement, which is the following. An adversary who corrupts any subset of the parties should not be able to learn anything about the honest party inputs, in this case here x1 and x4, beyond what it can anyways learn from the output of the circuit. And so this is a very general primitive with many applications. An example of a practical application, just to get an idea, is you have a set of hospitals with sensitive data about their patients who want to train some kind of statistical model on the joint data while maintaining their own patients' data as private as possible. So you can do this with multi-party computation, or MPC for short. And this is very well studied in classical cryptography. And a lot of this study focuses actually on a simpler primitive, which is known to imply MPC. And so this primitive is Oblivious transfer, which is just a very special case of multi-party computation. So in Oblivious transfer, there are only 2 parties. There's a sender who has as input 2 strings, S0 and S1, and a receiver who just has as input a bit, B. So the 2 parties interact, and at the end of this protocol, the receiver should obtain SB, so S sub B. So the security requirement is that the receiver shouldn't learn anything about the other string, so S1 minus B. So it should only learn the string that it asked for. And similarly, the sender should not learn anything about the choice bit B. So this is Oblivious transfer. And the nice thing is that this simple primitive is known to imply the full MPC for any functionality and any number of parties. Meaning that if you can construct a protocol for Oblivious transfer, then you can also construct a protocol for multi-party computation. And this result has actually been known for a while already. So we also know how to construct Oblivious transfer from various computational assumptions, like learning with errors, Diffie-Hellman, and others. So in the classical case, basically as a result, we know MPC from all of these assumptions, which is great. However, one of the general goals of cryptography, we can say, is to construct primitives from the weakest possible assumptions. And the existence of one-way functions is pretty much the weakest assumption that is known to be useful in cryptography. So one-way function, just to remind you, is simply a function that is easy to compute, but hard to invert on average. And now we can build many nice things from one-way functions, like pseudo-random generators, commitments, secret key encryption. But crucially, we know that one-way functions do not imply stronger primitives like public key encryption. And in fact, also, they don't imply oblivious transfer when they're used in a black box way. So this is a result by Impagliazzo and Rudic. And so using a one-way function in a black box way means not using its code, but rather just treating it like a black box in your protocol. So there's this black box separation in the classical setting, but moreover, we even don't really have any candidates for non-black box constructions of oblivious transfer from one-way functions. So this is the situation in the classical setting. I should also say that, it might seem to some of you that we are kind of splitting hairs here in the sense that we already have constructions of oblivious transfer from various assumptions that we believe to be true. So why should we care about constructing it from one-way functions? So the point is that these assumptions are qualitatively very different. So Diffie-Hellman and learning with errors, these are assumptions about the hardness of particular problems. The existence of one-way functions is much more generic. So we could, in principle, live in a world which Impagliazzo calls mini-crypt, in which one-way functions exist, but these other assumptions are false. And so what about in the quantum setting? So in the quantum setting, we again know that oblivious transfer suffices for multi-party computation. In fact, classical oblivious transfer suffices even for multi-party quantum computation, meaning that the parties and the adversaries could be quantum, and they could be computing quantum circuits on quantum inputs. But now one surprising and sort of exciting thing about the quantum world is that we actually have a template for building oblivious transfer, which I guess from here onwards I will call OT for short. So we have a template for building OT from bit commitment. And I'll describe what a bit commitment is soon. So this template crucially uses quantum communication. And we have known about these templates for a few decades already. It is from Crépeau and Kilian, and also studied by Bennett, Brassard, Crépeau, and Skubizewska. Now, unfortunately, this is just a template, which doesn't necessarily come with security proofs. So it was later shown that this template can be instantiated using the learning with errors assumption, although this implication here is something that we already had classically. And so what about doing things from one-way functions? So some of you might know that the bit commitments can be built from one-way functions. And in fact, it turns out that instantiating this template from one-way functions with just plain commitments gives a weak version of OT. And so without getting into sort of how this version is weak, in any case, this version, this weak OT is not known to be sufficient to get multi-party computation. And so prior to our work, this was the picture in the quantum setting, and it was an open question whether the standard OT can be constructed from just one-way functions. And so this work and the concurrent work of Grillo, Lin, Song, and Vaikunthanathan settled these questions by showing that one-way functions indeed imply OT, and so they also imply secure multi-party computation in the quantum setting. And so to put the classical and the quantum picture side by side succinctly, in the classical world, we have a black box separation between one-way functions and OT, and no plausible non-black box constructions either. In the quantum world, it was unclear whether one-way functions implied OT, and this is what our work and the concurrent work resolve. So, quantumly, a world in which one-way functions exist is one in which we get, even multi-party computation. And this implication here, in fact, only makes black box use of the one-way function, which is nice. Good. So then in the rest of the talk, we will focus on constructing OT from one-way functions. So before moving on, let me first be slightly more precise about how security of oblivious transfer is defined. So recall what the functionality is. The sender has two input strings, S0 and S1. The receiver has as input a bit B. They exchange a number of messages, and at the end of their interaction, the receiver should get SB. So informally, the security says that the receiver shouldn't be learning anything more than SB, and the sender shouldn't learn anything about B, about the choice B. So more precisely, we can consider security against a malicious receiver who deviates arbitrarily from the protocol specifications and at the end outputs some final state R out, which you can think of as what the malicious receiver has learned from all of this interaction. And security is formalized by saying that for any malicious receiver, there exists a simulator which interacts with an ideal oblivious transfer functionality here in the middle. So this is ideal in the sense that it behaves exactly as it should. So think of it as a trusted third party that gets the inputs from the two parties in the protocol and implements exactly the OT. And the output of this simulator, R out, should be computationally indistinguishable from that of the malicious receiver in the real protocol. So this is sometimes referred to as the real versus ideal framework for security. So I'll parse this a bit more slowly. So this definition basically, it's meant to capture the fact that whatever the receiver can learn in the real protocol, it could also have just as well learned in an ideal protocol, which is literally ideal and implemented by a trusted third party. And since the ideal protocol, of course, doesn't reveal anything more than it should, then the malicious receiver also doesn't learn anything in the real protocol. And so, yeah, I understand that it takes a moment to get around this if it's the first time that you hear about this type of security. So feel free to ask if I can, clarify something. Yeah, notice that actually this is a quite strong or restrictive notion of security. In particular, since the simulator here is interacting with the ideal OT functionality, just the syntax of this definition requires that the simulator extracts an implicit choice bit B from the receiver, because it has to provide some input to the ideal functionality. And so in order to get this simulation-based security for OT, the simulator needs to be able to extract inputs from the malicious party, for example, by interacting with it internally. And so one thing to note is that here the simulator has access to the internal state of the malicious receiver. And this access to the internal state is because we want to capture things that the malicious receiver could learn on its own in an ideal protocol. And we will see, in fact, that the simulator having access to the internal state of the receiver will be essential later. And then, security against a malicious sender is formalized in an analogous way, just with the roles flipped. Okay. Good. So we're now finally ready to talk about this template for OT using quantum communication. This is very similar to the BB84 protocol for key distribution. So if you're vaguely familiar with that, then you shouldn't have any problem following this. So in particular, this template for OT starts in exactly the same way, with the sender creating a bunch of BB84 states. So sampling a string of basis choices, either computational or Hadamard, denoted by C and H, and a string of encoded bits, which we will denote by X. So this X here specifies, right, whether the state is 0 or 1 if in the computational basis, and plus or minus if it's in the Hadamard. And then these states are sent over to the receiver. The receiver then, much like in the original BB84 protocol, picks a uniformly random string of basis choices theta prime, and then measures in this theta prime basis and gets some outcome x prime. Now, at this point, the sender reveals theta to the receiver, who can now sort of figure out which qubits were measured in the right basis, so in the same basis as theta. So here they're denoted in green, and which ones it measured in the wrong basis, in a different basis. And so the key here is that, for those qubits that the receiver measured in the right basis, it would have gotten outcomes that match the string X exactly, whereas it would have gotten uniformly random outcomes for the qubits measured in the different basis. And the other crucial fact, of course, is that the sender has no way to know which qubits were measured correctly and which were not, because theta prime is not being revealed here. And now, what the receiver does is it partitions the indices into two subsets, I0 and I1. In particular, it will set IB, so I sub B, where B is the receiver's choice bit, to be the subset of indices on which theta matches theta prime. So the indices that are in green here. And it will set the other subset, I1 minus B, to be the set of indices on which the basis does not match. And this, the receiver then communicates I0 and I1. And crucially, the sender here does not know which set contains the indices for the matching basis. The sender will similarly partition the string X into two parts according to the sets I0 and I1. And so, X0 will be the string, the substring with indices in I0. X1 will be the substring with indices in I1. And sort of the last step is that the sender uses this substring X0 to encrypt the first input string S0. And then it uses X1 to encrypt S1. Where here by encryption, I just mean something information theoretically hiding. Like, for example, applying a universal hash function to X0, using this just as a one-time pad to hide S0. If these are not terms that are familiar to you, just know that this encryption step is information theoretic. And these two encryptions are both sent to the receiver. And finally, the receiver knows XB. It knows one of the two substrings, the one corresponding to the subset in which it measured in the subset of indices in which it had matching bases. And it can use XB to decrypt and get the string SB. And so if the parties are honest here, this realizes our OT functionality. And now, sort of what is the intuition for security, right? So the sender has no clue about the bit B, because the two sets I0 and I1 here that it receives are distributed identically. Theta prime is sampled uniformly at random. It's never revealed. So the sender doesn't know on which indices the two parties had matching bases. On the other hand, for security against a malicious receiver, notice that the receiver will have measured in a matching basis at only about half of the locations. And so at least one of the two substrings, X0 or X1, should have high entropy from its point of view. And so the receiver will only be able to decrypt at most one of the two messages, which gives us OT. And so are we done then? Well, no, in fact, we are far from it still. So the issue here is that it's an issue that you might have heard about before. The issue is that the malicious receiver need not perform the measurement as prescribed. Right? Instead, it can just delay the measurement until after it gets theta. But then, of course, at that point, once it knows theta, it can measure in the theta basis and recover the whole string X. So the receiver will know both X0, it will know X1, and it will be able to obtain both of the two messages S0 and S0 and S1, which breaks the security of OT. So we definitely need to do something to fix this. So we need to force the receiver to measure at the right time. And we can do this by using a commitment. So let me have a very brief excursion to sort of tell you what a commitment is. So, right, a commitment you can think of as the cryptographic way of implementing a locked box. So here we have a committer on the left. So the committer can commit to a bit B by putting it inside a locked box and sending this to the receiver. And so the first property satisfied by the commitment is that it should be hiding. So meaning that the receiver shouldn't learn anything about the bit B by just looking at the box. And now at a later time, we would like the committer to be able to reveal what it committed to by sending some key that allows the receiver to open the box. And we want this commitment to be also binding in the sense that the committer shouldn't be able to change its mind on what it committed to. So there should be no way for the committer to open anything other than B. So these are the two basic properties that one requires usually of a bit commitment. Now note that the commit part here is depicted as a single message, but it can actually also be interactive. And in fact, it will be interactive for us, as we will see later. And so now we can use a bit commitment to enforce that the receiver measures when it's supposed to. And so the first part of the protocol will be the same as before. So the receiver creates and sends a bunch of BB84 states to the receiver. We ask the receiver to pick basis theta prime, measure in this basis. And now the only thing that we do different is we add the following measurement check subprotocol. So for each qubit, we ask the receiver to send a commitment to the measurement basis choices and the outcomes obtained. And the idea is now that the sender will test that the committed values are legitimate, they are consistent. And the sender will do this by picking a uniformly random subset of locations to test. For example, here, qubits 2 and 4. And it will ask the receiver to provide keys to open the boxes 2 and 4. And once it receives the keys for 2 and 4, oh, I don't know what happened there. It opens the commitments and it checks whether the reported bases match with theta. So whether the outcomes match with X. And so in this case, the basis was different for qubit 2, but it was the same for 4. And so the sender checks that the outcomes are the same. In this case, they are. So we call this subprotocol the measurement check subprotocol. And the rest of the protocol is then the same as before. The sender sends theta. The receiver partitions in the indices into two strings, I0 and I1, where IB will contain all of the indices where the bases match, sends I0 and I1. Then the sender encrypts using X0 and X1. And finally, the receiver can decrypt using whichever substring it knows. And the intuition for security here is that if this protocol is executed with a large number of qubits, and as long as the sender tests a large enough number of commitments, then if a receiver passes the measurement check protocol, it really must have measured. Right, and so one of the two substrings, X0 or X1, must have a lot of entropy from its point of view. So this commitment is just forcing a measurement. And so, then do commitments imply OT then? And by the way, as I mentioned, it is known that basic commitments can be built just from one-way functions. So then, does this mean that we are done at this point? And the answer is not quite, because proving the kind of security that we want is a bit more subtle. So recall how we define security. So we said that for any malicious receiver in the protocol, there should be a simulator which interacts only with the ideal OT functionality and outputs a computationally indistinguishable output. So in other words, anything that a malicious receiver can learn in the real protocol can also be learned by interacting with this ideal OT. And now also recall the observation that we made earlier, which is that the simulator just syntactically has to provide a bit B to the ideal functionality. So it has to be able to extract an implicit choice bit B from the receiver. In particular, just to get a better idea of what this type of security is saying, you can consider a special case of a receiver that behaves as an honest receiver with input B. Well, then, this receiver will obtain eventually SB at the end of the real protocol. And so the simulator must be able to extract B in order to obtain SB as well from the ideal OT functionality. There is no other way, right, for the simulator to get SB. And so, just to make things more concrete, the process on the top looks like this, right? We have a malicious receiver interacting in any way it wants in the real protocol, as long as it respects the syntax of the protocol. And at the end, outputting some information, which you can think of as what it has learned from the interaction. And then we have the ideal process, which has to simulate the same distribution of this output, R out at the bottom, by interacting with the ideal OT. And in particular here, the simulator can depend on the malicious receiver. It can, for instance, interact with it internally, right, by running a simulated version of the real protocol, for example, if it so wishes. So, for example, it could give BB84 states internally to the receiver, get back some commitments, run the measurement check protocol, reveal theta, and get some subsets of indices, I0 and I1. However, note that the commitments that the simulator has obtained here internally are supposed to be hiding. Right? And so it's not quite clear how the simulator can ever succeed at finding out B, which here would be equivalent to finding out which of I0 and I1 contains the indices for the matching basis. And in fact, if you think about it, notice that it shouldn't be possible to learn the choice bit B just by interacting with R, because otherwise the sender could also do exactly the same thing and learn B. And this, of course, would not be secure. So then, what gives? And the crucial part is that here the simulator has access to R's internal state. So it can do things like, for example, rewinding the malicious receiver. And so for a simulator that has access to the internal state of the receiver, all bets are off when it comes to the hiding property of the commitment. And it's at least in principle possible that the simulator may be able to violate this hiding property and find out the committed value. So open these boxes. And now this property of being able to extract a committed value when given access to the internal state of the committer, it can be formalized, and it is a stronger property than the basic requirement of hiding and binding. And we will talk about this property, which is called extractability, in just a moment. And so it turns out that this OT template can be proven secure when instantiated with a commitment which satisfies certain stronger properties. So one is precisely extractability, and the other is called equivocality, which we will see also next. So the moral of the story so far is that there is this template for OT from BB84 states, which uses commitments. However, plain commitments don't seem to suffice. And this is because the simulation-based security notion requires us to extract an implicit input from the malicious party. And the OT template can be shown to be sound, however, when the commitment satisfies these two stronger properties here. And so let's start from extractable commitments, which we have already mentioned a moment ago. So a commitment is extractable if, on top of satisfying the basic hiding and binding, it also satisfies the following. There exists an efficient extractor X here in blue, which has access to the internal state of the committer and is able to extract the implicit committed bit B. So again, you can think of this as being able to violate the hiding property when you're given access to the internal state of the committer. Now, what about equivocal commitments? So this, on the other hand, you can think of as being able to violate the binding property of the commitment when you have access to the internal state of the receiver. So in an equivocal commitment, there is an alternative way to commit. You think of this as an equivocal mode, and there is an equivocator here that is capable in the opening phase of opening this previous commitment to any value it wants. So and the value could be chosen after the commitment phase. So it breaks the binding property, but only when you have access to the internal state of the receiver. And so let's see these two new properties of commitment in action, how they help us prove security of our OT template. So given a malicious receiver in the OT protocol, a simulator can interact with it by playing the part of the sender, and it can obtain commitments and two subsets of indices I0 and I1, just like we saw before. It can then leverage the fact that the commitment is extractable in order to open those commitments and figure out which of the two sets, I0 and I1, contains the bases that are matching, the indices for the bases that are matching. And from this, it can just infer the choice bit B. So that's how the simulator extracts the choice bit B. And similarly, in order to prove security against a malicious sender, the simulator has to be able to extract the input strings as 0 and as 1. And we will leverage the equivocal property here of the commitment for this. So I will give myself a little bit more space to show you, how the simulator interacts internally with the sender to extract the two inputs. So the simulator here on the right, and this is sort of all happening inside the simulator. The simulator would run the whole OT protocol, playing the part of the receiver, except that it commits using the equivocal mode of the commitment. So this means that it can make up its mind later about the committed values. So it doesn't have to measure right away. It first waits to receive the subset of qubit locations that are tested and only measures those particular locations. And it can open the tested commitments to the appropriate values sort of after the fact by leveraging equivocality. And then once it receives theta, it measures the remaining qubits in the correct bases and is able to recover both S0 and S1. So this is how the simulator extracts the sender's inputs. And so, I realized that there are a few sort of moving pieces in all of this. So in case you kind of zone out a little bit, here is a recap of what we have discussed so far. So we have seen that there is a template for OT from commitments, and that this template is secure, where security means satisfying the simulation-based type security when it is instantiated using a stronger kind of commitment that is both extractable and equivocal. And so the question now is, can we build such a commitment? And so our result is that we construct a commitment that is both extractable and equivocal from a black box use of one-way functions. So, and given what we have discussed so far, the consequence of this is that oblivious transfer can be built from one-way functions. And so crucially, we give a quantum construction of the commitment. I think that previously people may have tried to construct such an extractable and equivocal commitment without success classically. But here the interaction in the commitment itself will involve quantum communication. So not only does the OT template already involve quantum communication for sending the BB84 states, but the commitment itself will require quantum communication. And there are two new building blocks that we develop in order to achieve all of this. The first is an equivocality compiler, meaning a transformation that turns any plain commitment into an equivocal 1. And the second building block is a transformation that turns any equivocal commitment into an extractable commitment. So it starts from an equivocal one, and what you get out is extractable, but not necessarily equivocal. And you can put together these two new building blocks in the following way. You can start from a plain commitment, which can be built from just one-way functions. And using a construction of Naor, we can then apply the the building block number 1, the equivocality compiler, to obtain an equivocal commitment. And then we can apply this equivocal to extractable transformation to obtain something that is extractable, but not necessarily equivocal. And finally, we apply the first building block again to turn the latter into something that is both extractable and equivocal at the same time. So this is a bit of a winding path. And the only thing to make sure for the last step is that this equivocality compiler preserves extractability, which it does. Now, the equivocality compiler is a bit technical, but not necessarily so insightful. On the other hand, the transformation from equivocal to extractable, so this middle step here, I find quite interesting because it reveals some kind of duality between equivocality and extractability. And this is also the step that involves quantum communication. So maybe let me just in a couple of minutes, I don't know how we're doing on time. I can.
So you have something like 8 minutes, including questions.
Okay, so let me spend just a couple of minutes to give you the idea for this. So the idea for this starts out by noticing that the OT template from Crepeau and Killian can be modified just slightly to obtain a template for commitments. So this is even easier than getting OT. It's a very simple template. We have on the left a committer who wants to commit to a bit B, and on the right a receiver for the commitment. And now the committer starts again by preparing a bunch of BB84 states and sending them to the receiver. And then the receiver picks a basis theta prime and measures in this basis. So far, this is just like a BB84, just like the OT template. And now at this point, the committer just simply reveals, in order to commit, it reveals theta and sends over an encryption of the bit B using X as the encryption key. So this is the commit phase. It's very simple, and the core idea is the same as for the OT template. So basically notice that because the receiver has measured in the basis theta prime, it has destroyed the information about X on about half of the locations. And so this encryption should be hiding because the receiver doesn't know, say, half of X. And now in order to open the committed bit B, the committer simply sends over X. And the receiver just checks that X matches X prime on the locations where they measured in the same basis. And if this check passes, the receiver is happy and uses X to decrypt and recover B. And so informally, this commitment is binding because even though the receiver has only recovered about half of the string X, the sender does not know which bits of X these are. And so the committer cannot really lie about X. Now, the issue here, of course, is the same as we face in the OT template, which is the receiver could delay the measurement until after it receives theta and break the hiding property in this case. And so we can again try to fix this with the measurement check subprotocol, asking the receiver to commit to the basis and measurement outcomes. But here there is an issue. We are trying to build a commitment, so we can't use a commitment in the measurement check protocol itself. So the point is we will use an equivocal commitment in the measurement check protocol, and what we will eventually obtain is an extractable commitment. And seeing that the resulting commitment is extractable is very similar to how we showed that we could get the inputs from a malicious OT sender. So the extractor here would just commit using the equivocal mode and use this to delay the measurement until after it sees where it's being tested. Okay, so just to conclude, I mean, one thing that it's easy to miss, basically, notice that once we plug our newly constructed commitment into the final OT, the protocol will have both parties sending BB84 states to each other, which I find quite interesting. So basically, the protocol will look like this. We have the sender in the OT sending the BB84 states, the receiver committing. But as we just saw, the extractable commitment here will involve the receiver also sending BB84 states. And so in the end, we have both parties sending BB84 states to each other, which is a bit unusual. Okay, I will stop here in case there are questions. Thank you.
So thank you very much. Yeah, sure.
Thank
Are there questions?